I'm going to talk to you now about slant asymptotes and let me just remind you where you're at. You're at calculus conundrums on limits by the perfect square, which is me. Okay, now we're going to talk about slant asymptotes here, and so I just want to show you a couple of examples. You only have a slant asymptote when the degree of the numerator is 1 greater than the degree of the denominator for rational functions. So on this function you would have a slant asymptote, and also on this function here the degree of the numerator is 1 greater than the degree of the denominator. Now you could have a vertical asymptote and a slant asymptote. Like this first function, you'll see that I'm going to have both. But you can't have a horizontal asymptote and a slant asymptote because, remember, if the degree of the numerator is larger than the degree of the denominator, then you're not going to have a horizontal asymptote. So these would have slant asymptotes, but they wouldn't have horizontal asymptotes. Now, how do you find a slant asymptote? Well, here's what you do. You have to think back to long division. So here's my function, okay? Now what I have to do is I have to divide the denominator into the numerator using long division. And so just think about how you do long division with numbers. If you're going to divide x plus 2 into 3x squared minus 1, what you would do is, first thing you do is say, okay, what do I multiply by x to get 3x squared? And that would be 3x. So you'd put 3x. And then you multiply this back by the divisor. So multiply 3x times x and you get 3x squared. Then multiply 3x times 2 and you get 6x. Now remember what you do, you have to subtract this quantity. So you subtract that quantity and the 3x squareds are going to cancel, and then you're going to have minus 6x. So bring down the minus 6x because there's no x terms up here. So you'd bring down the minus 6x and then you bring down the minus 1. And then you do it again. You say, okay, what times this x would give me a minus 6x to get this? So that would be minus 6. So you put a minus 6 here, then you multiply the minus 6 back times the divisor. So minus 6 times x would give me minus 6x. Minus 6 times 2 would give me minus 12. Now, when you subtract here, the minus 6x will cancel with plus 6x, and then you'll have minus 1 plus 12, which gives me 11. Okay, well that's the remainder because you can't divide x into 11, so that's as far as we can go. The slant asymptote is simply the quotient. It's the linear function that is the quotient. So in this example, the slant asymptote would be y equal 3x minus 6. Now, what you can do if you want to is go ahead and graph this function and graph this slant asymptote on the same graph, and you should have a picture like right here. You may have to zoom out to see it, but you should have a picture like this. Notice that as x goes to infinity, the y value goes to infinity, but look at the way it goes to infinity. It goes to infinity, but while it's going to infinity, it's getting closer and closer to this slant asymptote, 3x minus 6. Okay? Now, let's do another one. So oh, by the way, that one also had I didn't label it, I didn't highlight it on the graph, but that one also has a vertical asymptote. So if you just, draw a line, if you just draw a vertical line down through here, you'll see that you have a vertical asymptote. Okay, at actually -2. Vertical asymptote is x equal -2. All right, now this one, I'm going to do the same thing. I'm going to divide 3x squared plus 2 into 6x cubed minus 1. So I say, what times 3x squared gives me 6x cubed? That'd be 2x. Then I multiply back. 2x times 3x squared is 6x cubed. And then 2x times 2 gives me 4x. And then remember, I subtract this. And so when I subtract, the 6x cubed cancels with minus 6x cubed, and I get minus 4x, and then bring down the 1, I get minus 1. Well, since the degree of this is actually larger than the degree of this, I can't really multiply this by anything to give me minus 4x. So this is as far as I can go. So in this example, my slant asymptote would just be the line y equal 2x. So remember, your slant asymptote is just the quotient. It doesn't matter what the remainder is. So the slant asymptote is the quotient. So now you see this black graph, it just kind of goes up here and does a little dipsy-do and then continues upward. Okay, well this blue graph here is actually the slant asymptote. I probably should have made that a dotted graph, but that's the slant asymptote. So again, if you let x go to infinity, it gets closer and closer and closer to that slant asymptote. So that's really all I have to say about slant asymptotes. And so the last thing I'm going to discuss on limits is I'm going to show you a rule that some people teach, some people don't teach, but there's a rule called L'Hopital's rule that's helpful in finding limits of those indeterminate forms.